Good afternoon, everyone. So welcome to the IAS Distinguished Lecture Series. And I am Min from Department of Chemical and Biological Engineering and also Energy Institute. So today we are glad to have Dr. Khalil Amine with us. And Dr. Amine is actually our old friend. Okay? And he is a visiting professor of Department of Chemical and Biological Engineering. Also a senior visiting fellow of IAS, and also the advisory board member of Energy Institute. So on behalf of Department, Energy Institute, and also the IAS, we are glad to host Dr. Amine here. And he will be here about 4 weeks. So if you want to have an appointment, discuss with him, please arrange an appointment. Okay? So he will be glad to chat with you. Okay? Dr. Amine currently is a Argonne Distinguished Fellow and also Director of the Advanced Battery Technology team at Argonne, and is also a Director of the US-China Clean Energy Research Center. So Dr. Amine received a PhD degree from University of Bordeaux in 1989 in France, and then he moved to Japan to lead the development of various technology for universities and also for the private companies. So in 1998, he moved to Argonne to lead the development of advanced materials and battery systems for various applications. He actually is a well-known scientist, especially in the battery field. He has published over 490 peer-reviewed publications, and also filed and hold 186 patents. And he's one of the most cited scientists in the world in the field of battery, and currently is president of the IMLB and the chairman of the International Automotive Lithium Battery Association. He is an ECS fellow and also the European Academy of Science, just elected a member recently, and also the associate editor of Nano Energy. So this one is actually the impact factor now is over 13 now. He has received many awards, including the Scientific American Top Worldwide 50 Research Award, the University of Chicago Distinguished Scientist Award, and also the US Federal Laboratory Award. I think one of the awards that I want to highlight is the R&D 100 Award. He has received 5 times. And that award actually considered as the Oscar of technology and innovation. Okay. So without further ado, so let's welcome Dr. Amine to give us a lecture on the next generation lithium batteries and beyond. And welcome.
Thank you, Minhua, for this long introduction. It's really a pleasure to be here. I feel like this is my second home. And as Minhua mentioned, one of my tasks is to forge collaboration with many teams beside the department where I'm an adjunct professor. So please, if you need to talk to me, I'm here for the next 3 weeks, and I'll be happy to talk to you and share information with you if you need. So today I would like to talk about what we're doing at Argonne to advance electrification. Argonne is a US Department of Energy lab, and our main task is to develop advanced energy storage system, mostly for electric vehicle. But if you can do that, you can always spin it to grid application and other applications. So let me start with this. This is the human top 10 problems for the next 50 years. So you can see it's not water or food. Energy is the main concern. And the reason is within the next 50 years, the population will pretty much close to doubling to 10 billion. And the demand for energy will move from 14 terawatt to 28. And if you look at the source of energy at the moment, it's still dominated by petroleum, coal, and natural gas. Nuclear energy is not popular at the moment, but the renewable, as you can see, is the lowest. And if you look at the different renewable, most of it is hydroelectric and biomass. The solar and wind are very small. And one of the reasons is because there is no cheap, reliable, and efficient energy storage system to capture that energy and store it. You can see it also in this next one. You see most of the renewable participate very limited to the most of the energy resource for residential, commercial, and industrial. The big one are oil, natural gas, and coal. For transportation, which is most important to us, the source of energy is oil, and the story doesn't end up here because half of the energy is wasted in heat. So you use one source and you waste half of it. So the situation is very unsustainable. In the United States, I think I've showed this before, we consume about 20 million barrels a day, and 72% of that oil goes to transportation. So if you really want to make an impact, you have to advance electric vehicle in a commercial scale. The same things with China. China, this is the trend of vehicle production. You can see China is actually already overtaken US as the main producer of vehicles. And by 2020, they'll be producing over 25 million. And China actually import more oil than the United States. Actually, United States now, they actually export oil. So the situation is getting very, very serious. Another reason why electrification is very critical is the greenhouse gas emission. This is the atmospheric CO2 concentration. If you stay business as usual, you will see that the concentration of CO2 will go to 700 ppm, and that translates to almost 4-degree increase in the Earth temperature. So obviously the consequence here will be the climate change will be very, very severe. But fortunately, the electrification is underway. You can see it now. You can see a lot of Tesla actually in Hong Kong, which is interesting. And one of the main reasons is this, the regulatory requirement that was set by mostly Europe and China. United States had dropped this requirement thanks to our, I have to be careful because there is a video, our president. But it doesn't matter because China is driving the electric vehicle. The requirement for China is 56 miles per gallon by 2020, in 2 years' time. It's not that much. There is also talk in China that they're banning actually the conventional engine within the next 15 years. Europe is a little more aggressive. It's 58 miles per gallon within the next 3 years. The reason why I say it doesn't matter because every single company in the world produces cars in China. So if they do it, GM, Ford, Chrysler produce cars in China. If they do it in China, they will just sell it in US. So I don't see an issue. So electric vehicle is moving forward. And there are a whole bunch of, here is the, one of the Bloomberg forecasts for electric vehicle. This is actually very conservative because I was last week in Germany and I met the CTO of Volkswagen. And Volkswagen has actually announced that by 2025, 25% of their fleet will be electric vehicle produced. So if that thing is happening, this number will be much bigger. But the expectation is that within the next 15 years, you will see over 35 to 40% of electric vehicle in the market. So this is very, penetration will be very significant. And again, there are many types of electric vehicle. You have the hybrid, which is the most popular. Actually, you can see millions of vehicles now in the United States. We have over 7 million hybrid vehicles being actually sold in the United States alone. The reason why it's very, very popular because it's very cheap. The investment is very small, powerful battery, and not energetic. Usually 10% of the energy of this battery mostly to assist the main engine and recover the energy then in regenerative braking. So you don't have to charge your battery. So that's very convenient and cheap. You can buy now a Prius in the United States for $18,000, and Toyota is making money out of it. The other system, which is much more complicated, is the plug-in. The plug-in in the United States, the target is 40 miles because the average commuter in the United States commute within 40 miles, about 78% of those. But the technology here is very complicated. You still have an internal combustion engine. You have several electric motors, depending if you want to have full drive, four-wheel drive, or two-wheel drive. You have a gas tank, you have a transmission, and you have a large battery. So all of these are concentrated within a certain volume. So the battery has to be big enough to allow you to go all electric for 40 miles. before you can switch to a hybrid in case you decide to go somewhere else, or you can go home and charge. So obviously the demand on energy for the battery is very, very severe in this case, much more severe than the electric vehicle. The electric vehicle, you just have basically an electric motor and a battery. All the other things is taken out. So you have plenty of space to put a high energy battery there to allow you to go longer electric drive range. But the popular one mostly use nickel metal hydride battery, which is a technology that is very low energy but is very powerful. You can basically boost very quickly in this case. So if you want to go to electric or plug-in, you really have to move away from this technology because it's low energy, as you can see, and that's why lithium-ion is very attractive. It does have higher volumetric and gravimetric energy density. You can make it lighter, smaller, but yet very energetic. And you can see the square is very broad. You have a whole bunch of different chemistry to select from. So for the past 30 years, there is plenty of system that's being developed, both at the cathode, anode, electrolyte, and so on. The application obviously is very, very broad. Lithium-ion has basically dominated the consumer electronics. So every single consumer electronic you are basically operating use lithium-ion now. The next step is automotive, and we start seeing that at the moment with there's about 20 models in the United States that use lithium-ion for hybrid and plug-in hybrid and electric vehicle. I'm sure in China there are a lot that use iron phosphate. And the biggest things will be, of course, the grid. So I'm glad to see that you guys got a big program, try to develop storage for grid applications. So one of the reasons why the expansion is still not very significant for electric vehicle and plug-in is the cost. If you ask the car companies, the cost is the biggest barrier. You can buy a Tesla now if you can afford it, but not everyone can buy a Tesla. I know how much it costs in Hong Kong, but it's, in the United States, go buy $120,000. Yeah, so cost is critical. Safety and life, I think the companies have already made tremendous progress. You don't see a lot of cars burning. And then you have energy. Energy and costs are connected, and here is the reason why. If you have a battery that is that much energy with that much volume and weight, this is basically a Nissan Leaf pack. If you are able to advance or increase the energy density of the chemistry inside this battery, you can make it smaller, but yet the same energy density at the pack level. Now you have less materials across the board. That's a real way of reducing the cost. Remember that. Taking a cathode A to a cathode B, like moving from a cobalt system to iron-based system, will not make a major impact because the cost of a cathode is only 10% at the pack level. So remember that if you really want to make an impact on cost, you have to increase the energy of the whole system. So how to increase the energy? You can do that by increasing the cathode capacity. These are the conventional capacities at the moment. Moving to this, basically increasing by 80%. You can do that by the anode as well. Now moving from the graphite, which is used at the moment as the anode of choice for the past 30 years. And there is a lot of effort now to try to move to metal or metal oxide-based antimetallic composite anodes. So in that case, you have an opportunity of increasing the energy density by 300%. So by coupling these two systems, you can make a significant impact in the energy density of the full system. So I'm going to give you an example of things that we develop, and is going to see it in the market that has been actually licensed by several big companies. And there is a big effort to scale up what I'm going to show you. And then I'm going to mostly focus on beyond lithium-ion, because I know that some people here are working on sulfur and lithium-air, so I'll show you some exciting work there. Okay, let's start with the cathode. Now, if you take, for example, the NCA, this is the Tesla technology. They use a very high concentration of nickel. When you charge this system at high voltage, let's see 4.2 volt, you can pull out a lot of capacity out of this system. If you go higher in voltage, you can get almost close to the theoretical value, but the problem is at this level, the material is very unstable, so it decomposes the electrolyte. Here is an example. If you charge to 4.5 volts, you get very large capacity, almost 230 milliampere per gram. But then if you cycle it, it drops very quickly. So you get the energy, but you lose the cycle life, which is a problem. So one of the reasons why the cycle life is basically compromised, we look at a material or an electrode here, once we disassemble the cell, and take one particle and microtoom it in half and look at it by high-resolution transmission electron microscopy to see what is happening at the surface. And this is what you get. You have the layers where lithium is basically sandwiched between the layers, and then you have another phase and another surface film. So through electron diffraction, this phase is nickel oxide. This one is basically R3 layered oxide. So what happens is when you take this material, you remove lithium at high voltage, you create this phase, which is thermodynamically unstable. Nickel 4 plus doesn't exist in an oxide phase. You have manganese oxide is a 4 plus, but nickel, it always reduces immediately and generate oxygen. So this phase here is nickel oxide, that's what you see here, and the oxygen react with the electrolyte and give you a surface film. Now we have a very large SCI where lithium has to struggle to go through it during charge and discharge. And as a result, you lose capacity because your interfacial impedance grows significantly. That's how you lose the cycle life. Now, what we learn from all this is that when you use a very high nickel concentration in a cathode, you get very high capacity. But then you have a problem with cycle life. So to address this, we developed this material that now has been licensed and is being mass scale up for application in electric vehicle. We call it a full gradient cathode material. This is the first time where you have a material that has many composition across the particle. You start nickel rich to give you the energy and slowly reduce it and increase the manganese to get more stability at the surface that prevent that reactivity with the electrolyte I showed you. So a very clever approach by engineering the particle. And the reason why we go slowly, because there are volume changes. So if you make a big composition change quickly, you create a different gap in volume, and then you have a kind of separation. So you have to be careful about that. So that's the reason why we did a full gradient. The full gradient will allow you to put as much manganese depending on the particle size. So how you make it? That's the next step. Could you scale it up? And you can just use a simple co-precipitation. This is a very well scalable and mass-produced technology for the NMCs and the NCAs that I told you. In the case of nickel manganese cobalt that is commercially available for automotive now and consumer electronic, they use only this. They put 3 metals with defined composition in a sulfate form, and they send it to the reactor. You have a chelating agent and a co-precipitating agent, and you make basically particles. So with this new approach, you just add one more tank. That's your investment. One tank that has nickel rich, so you can put the nickel first in the bulk, and then one tank that has manganese rich. Cobalt can be the same composition if you want to keep it constant across the particle. And then once you start moving the nickel to the reactor, you basically dilute the nickel with manganese and sand both. With time, you're changing the composition. So one company that the license have already scaled up this material to 10 ton a day. So there is some serious work going on now. Here is the comparison between the existing technology that is in the electric vehicle now, like in BMW or the Chevy Bolt from GM. They use the 622 nickel manganese cobalt with 6% nickel. If you look at they're both made by co-precipitation now. This one is spherical in both cases, but if you look at the primary particle, in this case, they are spherical, small, where lithium will go through the grain boundaries. In this case, we have rods, so it's very different, but dense rods. That's the reason why the density is higher. This is the same composition. This is the same average composition because the composition here is changing with from the burr going to the surface. Remember that. But the reason why we have high density is because of this structure. It's totally different from here. Now, density means energy. because you pack more active material in the electrode, keyword. The energy is capacity, voltage, and density. Remember that. If you use a nanomaterial, then you drop your density significantly, and therefore your capacity at the electrode level significantly as well. The other things we've seen is that the gradient approach is also at the primary particle. If you look at the composition here, it's changing as well. So it's not only at the secondary particle, but the most important things of all this is this. This is a TM that shows this road here, the layers are parallel to the road, which means lithium will fly out quickly. And that's key to fast charging and discharging of the system. So you move lithium faster, which means at the same potential, you may move more lithium here than here, because here the lithium has to go to the grain boundaries, so you don't move as much. Which means the capacity of this material at the same cutoff potential or voltage will be higher here than here. And actually, we've proven that. This is the capacity using exactly the same condition. With the commercial NMC 622, we get about 178 at about 4.3 volt cutoff. Here we get about 225 because of that specific morphology, which is very critical. So morphology of material can also impact the performance of the material. Remember that. So eventually after that, we start looking at what is the performance at the full cell. And this is a small 25 milliamp hour that we made power cell we made at Argonne, and we compared the performance at 4.3 volt. You can see that the commercial one is dropping pretty fast. Within 300 cycles, we lost almost 25% of the capacity. With the new gradient, we have far much better result. We also work with the industry and build bigger cells. Well, let me show you. Of course, one of the other reason why we're trying to stabilize the surface is to enhance the cycle life, but also enhance the safety, because oxygen reaction with the electrolyte is exothermic, and therefore you can create a thermal runaway if you don't control it. So this is a DSC of these two materials, so we compare apple to apple. You can see clearly that in the case of NMC, when you fully charge it to 4.3 volt and then react it with the electrolyte, the enthalpy of reaction is higher, about 1,000. And the onset temperature is also higher, better than the NCA, but it's lower than in this case here, where you have half the energy and higher onset temperature. So the safety of this material is much better as well. So we hit two birds with one stone. We improved the cycle life, we increased the energy, and then we increased the safety. I say three birds, I would say. We also looked at much higher concentration of nickel, 8, because here you get much higher capacity, obviously. And we built cells. These are basically 2 amp hour cells, well balanced with an electrolyte additives, because we operate at high temperature. And you can see we use the Umicore, which is very popular as the reference material, and our full gradient at the same composition. And you can see the conventional one that is under development by the auto industry drop very fast, because now you have more nickel. Therefore, the reactivity is much higher, while the new material is much, much more stable. Both at room temperature, even the performance at high temperature is better than the performance of the commercial one at room temperature. So this is very important. The reason why I say this is very important, if you look at Tesla use NCA, which is 80%. And you notice they don't use big cells, because that material is very unsafe. If you have large cell, it will explode. They use small cells. There was 1,000, I think about 8,000 of them. If you go and look at under the hood of Tesla, you see about 8,000, 18,650. That's the reason why they develop, they're very smart. They develop a matrix design to control all these thousands of cells. But when you have thousands of cells, the cost is very high, and that's the reason why Tesla is expensive. But imagine if you switch that material with this one here, where the safety is better, the energy is higher. We did a calculation, we dropped the number of cells from 8,000 to about 4,500. That's a significant cost reduction, because you can increase the size from 1860 to a D size, for example, from like 5 amp hour to 10 amp hour. With this system, you don't have an issue with safety. So this is an opportunity why large companies are looking at this technology at the moment. So that's, and this is a real safety data of this material here. You can see it when you do the overcharge, the temperature increased only by like 5 degrees C. And if you look at the nail penetration, basically you charge your cell and then you hit it with the nail, you short it. The increase in the temperature is almost similar to the iron phosphate. It went up by 70 degrees C also, only. So those are very real tests at the battery level. So now I'm going to show you the other way of increasing the energy density. And I'm going to share with you some new data on the pre-lithiation, is to move away from intercalation using graphite to alloying or conversion reaction at the anode side. Remember, we can increase the energy by increasing the capacity at the cathode, but also we can do that at the anode. Here is an example at the anode. You have a whole bunch of metals that you can alloy lithium with. And obviously, silicon is the most attractive because it's dirt cheap. You have plenty of it in the earth. And it also gives you the higher volumetric and gravimetric energy density than other metals. It's almost 10 times graphite. So obviously, you're not going to use all this. And I'll explain why. But if we can just, the reason is simple. Using that much, you have no cathode to match this energy, this capacity at the anode side. It's impossible. You have to make 1 millimeter thick cathode if you want to go there. Unfortunately, when you do the alloying, you get a lot of capacity, but you have huge expansion, volume-wise, almost 400%. That's not good. If you have a big expansion, you expect, after cycling, cracking of the particles and isolation. So when you isolate your particle, you lose conductivity, and that particle is dead. So your capacity will drop very quickly. So that's the problem. I think I have a video that shows an AFM, an in-situ AFM, where we basically cycle and look at the surface of the particle by AFM to see what is happening, see if it's going to work. Okay, so if you check out that red point here, at the moment we are not alloying because we are not really cycling, but this is the reference and this is the scan one that we are observing. So once this one start alloying, when it start coming here, you will observe what happened. This is in first cycle. So you can see now when it start alloying, you can see the cracking start happening because of the expansion. And you can see it right there. And it will go back, and with time, it will start isolating. So that's an issue that needs to be addressed. Many work has been done in the literature where you can see basically by what they do is by incorporating silicon in carbon matrix to keep conductivity. But so they put it in silicon fiber, and how they can incorporate silicon in carbon fiber. The nanotubes, my colleagues at Stanford, they use the York shell type where they can incorporate the silicon inside the carbon spheres and so on. But all this, they show a very good result. I'm not sure about this result because the loading is very small. It's like using shallow charge and discharge. So one has to be very careful. If you guys doing work on batteries, you have to set up, the condition of testing. It's really important. If you really want to compare apple to apple, that's what we did at DOE. All the program that is funded by DOE on silicon, we have clear condition of how you make the electrode and how you test it. So you can test apple to apple. The only things that is in common of all this is they are not scalable. And that's the reason why you see most of the industry is just mixing 90% of graphite with maybe 5% of silicon to get maybe 20% increase in the energy density. That's what, if you look at Panasonic and others, that's what they do, and the Korean and Chinese. Yeah. So I'm going to show you an example of a new process that has been also has been licensed and is in process of being scaled up by a German company at the moment. So the idea is actually when I visited a silicon wafer company in Silicon Valley, we were talking about this concern. This is a very dangerous gas. That's the main source of making silicon wafer. They make thousands of tons of this material. The only problem when they send it, to make silicon wafer, they contaminate it. And for silicon wafer, you have to have pure. So basically the byproduct is huge, about 80% is byproduct waste. And they struggle to get rid of it because this is a dangerous gas. So you really have to have very special tools to take care of it. So in our case, we thought, okay, well, we can use it as a byproduct. The silicon fair will give it to you for free because they will reduce the cost of getting rid of it. And then basically use graphene by exfoliating graphite using acid, very disordered. It doesn't have to be fancy monolayer, whatever, just like this. And graphene has sheet, so you put this in a reactor and you reduce this gas. This is a gas, gas go everywhere, obviously. You reduce it and you form silicon. And since you do that at the gas phase, the silicon particles are already at the nano phase. So nano does not crack immediately. It will take longer to crack, obviously. So the idea here is when there is cracking, with the pressure of the cell, those sheets, which are conductor, will collapse on those cracked particles and keep conductivity. So you don't lose, you don't isolate the particle. And here is an example where you can see without and with the graphene sheet. We're also seeing, this is another issue that I'll talk about. The efficiency is better, it's only 85%, but it's not as good as carbon. Carbon is almost 98%, and that creates another issue that we'll come back and talk about it. And you can also design your gas to minimize the amount of silicon in graphene or increase it. So here is an example where we get initially targeting 600 milliampere hours, very good. We have actually 1,000 cycles with this at very high loading at 1C rate. So this is how it works in the silicon wafer. They have these tanks full of this gas. So they capture the byproduct, which is a contaminated trichlorosilane. And then what you do, basically throw in graphene and heat it up at low temperature, drop in 10% of hydrogen, and then you form your material. Very simple. You hit two birds with one stone. You get rid of this dangerous gas, and you make a useful material out of it. And one of these companies has licensed it, and now they are in the process of mass scaling it. So you may see it actually next year. So here is the other problem with silicon, is the poor efficiency there in the first cycle. Now, this is a discharge. The charge is about 1,700, and the discharge is 1,500. So the difference is about 200 milliampere per gram. This is one of the best samples, by the way. There are samples that have more than that. So imagine 200 milliampere per grams. If you use the concept of carbon, carbon is about 98% efficiency, and is only 360 milliampere per gram. So 2% out of 300, you can easily use the cathode to design an excess amount of cathode to take care of that irreversible loss. Here is it. In the case of graphite, is 90%. So it's okay to use excess cathode, the lithium, to compensate for that irreversible loss. But in case of silicon, the capacity can vary between this, and the efficiency is low. There is no way you can use a large amount of cathode. You need pretty much double the capacity of excess cathode just to compensate for the first irreversible loss. So cathode is expensive and heavy, so your overall energy will drop significantly. So that's not a way to go. But I'm going to show you a very clever way of doing it based on our lithium-air work, actually. If you use lithium, if you use a cathode, that's the capacity. Use a lot of it, heavy, expensive. If you use lithium, the capacity is very high. It's lightweight material, almost 1,600. So, if you are able to, unlike most of the people, they try to add lithium to the silicon and add electrolyte to basically suck the lithium inside the silicon to take care of the initial efficiency. Here, you take lithium, you mix it with the cathode, and you activate it, and you send lithium to the anode. It's a very different approach. So you can use this, or you can use lithium peroxide. Lithium peroxide will give you twice this energy, so each amount of the material will be much, much more smaller. Here is an example. We take a high energy cathode, we add small amount of lithium, you see we get huge capacity. Just 1%, you get almost 300 milliampere per gram. Obviously, you may think we are operating at high voltage, and therefore this could be just a decomposition of the electrolyte. So to prove that, we actually taken it LTO. LTO has 100% efficiency. So you can design your cell to get you the capacity you need. For example, in the case of high energy cathode, you can design LTO to match it, and you get about 250. That's the capacity of the cathode. So if you add 1% of lithium, you can see there is a huge capacity, and you recover it at the LTO, which means that lithium really comes from that lithium. Huh? And we took in an example of a poor efficiency material that has 70%. We use it without lithium. You can see we use a cathode that should give us 250 milliampere per gram. That's the high energy lithium-rich, manganese-rich cathode. But we got only 176 because we lost a lot of it to the silicon to take care of the irreversible loss. We add 1% lithium, and you can see we recover all the capacity of cathode because the lithium was able to provide the lithium to the silicon, and then now you can cycle the capacity of the cathode easily. So this one also has been licensed because it's very simple. It's cheap, just 1% of material that is commercially available. So if you take all these technologies and then put them together, this is a company design, you actually can achieve 350 watt-hour per kilogram and 1,000 watt-hour per liter with this system. That's an increase of almost 80% versus the Tesla technology, right there. And at Argonne, we do have what we call Backpack. I think this is an open source. You can actually download it and use it. This is very nice because it has a huge design that goes all the way to cost. So you can design the whole pack. You take your chemistry, you put some parameter, and we'll tell you where that chemistry stands versus existing technology. Yeah? And it will also tell you the cost. And here is what come out of this design. For example, the conventional system, which is NMC with graphite, the cost of the usable energy in a vehicle is about $220 per kilowatt hour. That's too high. The target is 125 at the moment here. And then we start changing, go into high energy cathode to silicon, you'll be here. So if this is where we are without pre-lithiation, if you do the pre-lithiation, you drop to 100 watt-hour per kilowatt hour. So this technology can achieve the cost that we are targeting now. But then if you look beside this, if you look at the sulfur or lithium air closed system, you can talk about $75 or $70 per kilowatt hour. This is really attractive. So how can we enable this system? So I'm going to address an example on sulfur and an example on lithium air. Okay, why sulfur? Sulfur obviously is dirt cheap. I think you can buy it for $28 a ton. As a matter of fact, if you go to Saudi Arabia, they have mountains of it because it's a byproduct of the petroleum industry. Yeah. That's one reason. And the other reason is it has very high gravimetric energy density, 3 times lithium-ion. Not only cheap, but it gives you 3 times more energy. And one of the reasons why it gives you that much energy because it's a 2 electron reaction, not 1. During the discharge, you have multiple phases, polysulfide that is formed. And that's a problem. I'm going to summarize all this issue here. You can see these are the challenges. One of the problems is sulfur is insulating. It's 10 minus 30. So you really have to put a lot of carbon to create some conductivity at the electrode level. So if you do that, you're going to use a lot of inactive material, and that can drop the capacity. Huh? Some people, they use 50%. So you have to maximize the active material in your electrode to get the energy you need. So that's not good. The other things is you have to figure out a way to put high loading. That's one of the problems with sulfur. And then there is an expansion of volume when you move from sulfur to Li2S, for instance, almost 80%. You have to take care of that as well. And then you have the polysulfide that dissolve, and then they tend to actually, shuttle to the anode and then stays there. And that's loss of active material. You're losing sulfur. And the other big problem is lithium metal. The dendrite issue with lithium metal, that is a big issue. So you can see this is a very challenging system. So I'm going to show you, at least at the cathode side, we're able to take care of conductivity and dissolution issue, which are 2 major problems. at the moment, most of the people, if you look at all the literature, pretty much without exception, and one advice to you guys, you have to think beside the box. You know, if you just follow what the other guy is doing, you're going to just be late because they've already done it. Huh? So if you look at all the literature, that's what they do. They incorporate sulfur in carbon matrix to create conductivity or to try to encapsulate the electrolyte, so to basically immobilize the polysulfide, which doesn't make sense because it dissolves in the electrolyte. And once it dissolves, it will shift. It will shuttle between the cathode and anode. So it doesn't make sense. You know. And they use all kind of carbon, you know, mesoporous carbon or microporous carbon or spherical carbon where it can impregnate. Yeah. Here are some examples, for example, of some famous work that's been done where they incorporate sulfur in spherical carbon or in basically mesoporous carbon, like Linda did. And they show some limited capacity improvement with few cycles. Now, I'm going to show you a different way. If you look at the periodic table, sulfur is here and selenium is here. If you look at sulfur, you get high capacity, but the density is lower. Volumetric capacity is that much. Very insulating, which means you have to put a lot of active carbon to create conductivity. And it melts at very low temperature. You have to worry about that. Because if your temperature of cells goes up beyond 115, you will melt your sulfur and basically short the whole system. Huh? Now look at selenium. Selenium has low capacity, but high density, so volumetric energy is the same. But look at the conductivity. It's 20 order of magnitude higher. So that should take care of the conductivity. And then the melting point is much higher, which means you have to worry about lithium metal before you can worry about this. So the idea here is to, obviously, one of the problems that I didn't show here, I should put it to be honest, selenium is $60 a kilogram, which is, you can buy 3 tons of sulfur with that. Huh? So that's the problem. The cost is an issue. But $60 is not that far from lithium cobalt oxide, which is about $50 at the moment. Huh? But it's not, you know, in automotive, it's unacceptable. So the good news is there are many phase diagrams of selenium and sulfur. You can select between the two. And here is an example where we looked at sulfur 7 and selenium, and we did some cycling. It gives us pretty much the same performance as sulfur when you use ether-based electrolyte. That was not very interesting because when you have these multi-phase, it means you may have dissolution of polysulfide or polyselenite. And you get fairly good capacities, as you can see here. This is the first shot. One of the reasons why we get in better performance here without putting, we put in about 80% of this active material, is because of the conductivity that the selenium add to the system. Huh? So the first thing we want to know, is there any polysulfide or polyselenide dissolved in the electrolyte? And there are not too many techniques out there to do that, but at the advanced photon source at Argonne, because X-ray will give you just look at crystalline phase. In this case, you get mostly amorphous, so you don't get much information. But you can use Xanis. Xanis is a very good technique to look at the oxidation state, and it can give you that information at the crystalline phase, amorphous phase, and liquid. So you can look, actually, you can probe the electrolyte and the concentration of the polysulfide and polyselenide and their oxidation state as well. So they're in operation. So we do have this technique that we developed, and here is what you get. You get thousands, this basically you're cycling, you get almost thousands of spectra because you plot spectra within less than 1 minute, maybe 40 seconds you have one Xanis spectra, basically. So these are many, many spectra coming in. So you can see when you do that, during discharge, you see your Xanis spectra is shifting toward low energy, which means you are changing oxidation state. You're reducing, you're forming this polysulfide. And these are probed in the electrolyte. So there is a dissolution happening where the oxidation state of these different phases can be clearly seen here. If there is no oxidation state changes, it should be flat. And we were able also to fit this. If this is a spectra, this is just one, huh? One Xanis spectra. So basically, here is what you've seen, and then you have plenty of them. It's a lot of data here. I mean, just to to go through all this data, it takes a long time, actually. So when you basically just try to fit it with two-phase without any dissolution, it doesn't fit well, obviously. But when you add the polysulfide, it fits very well. Then you have a program to tell you at what phase is starting and what time it disappears, for instance. So that's a problem. You know, we were very disappointed because we were able to improve the performance with putting high excess of the active material, but there is a dissolution, and therefore your capacity failed eventually. Then when we run the carbonate-based electrolyte, we've seen a different story. See, it's flat. We don't see those multiple phases in this, but the polarization is very high. So the performance was very poor because the impedance was very high with the carbonate. Now what we learn here is that if you use a different electrolyte, the story is different. So now we have a hope. We need to find that electrolyte that can work with this new system. And you see the fitting is just two phases, in this case with the carbonate, but the dissolution does not exist here, and we did actually a dissolution experiment. If you take a carbonate and use polysulfide, it doesn't dissolve, you can see. When you use the ether-based electrolyte, it dissolves. So we confirm that with carbonate, there is no dissolution, but with the ether-based, there is dissolution. So now what we need to do is design a new electrolyte that works, and we did. Here is a new electrolyte. We call it NL1 because we are patenting it now. I promise I will share it with you later. If you use, you can see clearly the pattern of the discharge is different to start with. That's great because that tells you have a two-phase, a one-phase reaction, basically, moving from sulfur or selenium-sulfur to Li2 selenium-sulfur, if you want. And we did an experiment that shows that there is no dissolution versus ether base. So now we need to know if this material works. And so we incorporated in carbon. We put about 10% of carbon with this system, so you can see the dispersion of carbon. But we don't put 50 or 60%, just 10% like in lithium-ion configuration. We run the Xanis is very flat, so we don't have any shift, which means there is no dissolution. This is the most important experiment because in the naked eye, there might be some dissolution. You're not going to see it, huh? Yeah, because the color didn't change. It doesn't mean there is no dissolution. But here you are probing the liquid inside the cell. They're in operation, and you don't see any shift that basically dictate we have a change in the oxidation state of these phases. Huh? And okay, we did this. And then you can see also when you run just a normal a CV, this one has multiple phases. This one has single phase, clearly. Obviously, here is amorphous. You don't see much. You don't get any more information with X-rays. This is hard X-rays. That's also one spectra is 1 minute. But even though with very high intensity, material is amorphous, so we don't see much information on structure. We did some DFT calculation to see why we don't dissolve these polyselenide or polysulfide in this electrolyte. You can see the energetic is very high. So the barriers with this new electrolyte does not allow for dissolution of these phases. So now we have a selenium-sulfur that gives us conductivity, and we have this electrolyte that prevents dissolution. So we cycle it, and you can see this is the ether base. You have a big polarization because of the shuttle effect. This one basically doesn't have any shuttle effects, so, and it's cycled very well. Obviously, this is 5 sulfur for 1 selenium. We looked at a whole bunch of phase diagram, and we looked at this one where we have no dopant. Selenium is really a dopant, so very small quantities. You're almost close to sulfur, 90% versus sulfur. So capacity-wise, almost similar. And this is what we got, you know, because here we are able to put high concentration or high ratio of active material, almost 80% versus 50% here for the, and we operate at 1C rate and a different rate. You can see clearly that this new system outperforms sulfur better without dissolution. So we're now trying to work with the industry to prove this concept in a full cell. Of course, we do have an issue of lithium metal, and so that need to be addressed. DOE has now a $10 million program just to address the lithium metal problem that is run by PNNL And hopefully they will be able to fix this problem. Let's make this system very practical. Okay, so now the last part is lithium air. Obviously, lithium air has totally different configuration versus lithium-ion. Lithium-ion is an intercalation process between carbon and metal oxide. Here you have an electrode, which is porous carbon, and you put a catalyst. So basically what you do, you send oxygen, you have 2 electron transfer to form lithium peroxide. That reaction gives you 10 times the energy of lithium-ion. Now, that's very serious, 10 times. If you can just tap into 30% of that reaction, you get almost 3 times. Huh? This is how it works. For people who don't know, basically when you start discharging, you have the first electron transfer to form a superoxide, and then the second electron transfer to form a peroxide. And then during charge, you basically dissociate those bonds, which is extremely difficult because the peroxide is resistive, insulating. Huh? So when you do the charge, you move the first electron to dissociate the first bond and then the second bond, and you end up with oxygen out. So basically, in another word, use air while driving, if you use it in an electric vehicle, and release oxygen while being charged. Can be better. Huh? But there are so many problems with this system. You can see the polarization is huge. You basically cycle for 10 times, it die. One of the reasons when you form a discharge product, which is a peroxide, is very corrosive. It attacks the electrolyte and destroy it. You have oxygen crossover that react with the lithium metal, form lithium hydroxide, so you completely lose your anode. So that's why you die quickly. The peroxide does not dissolve in the electrolyte, so it stays and it clogs the pores of the cathode, and for now oxygen has difficulty moving in, so the feed become very low. These are just few examples. You still have lithium dendrite from lithium metal and so on. So clearly, the good news is there is a lot of people, actually the papers on lithium air is increasing significantly. There's a lot of interesting things to look at. So I'm going to show you a way to a new system. So these are the ideal reaction for lithium air. You can have the first electron transfer to a superoxide radical that can react with the electrolyte, very corrosive. Or if you have if it reacts with lithium, you form a lithium superoxide. So lithium superoxide is interesting because it's conductive, so you can easily dissociate that bond, and is less benign as corrosive agent versus peroxide. So if you are able to stabilize this system, you are in good shape. The problem is, if you look at the literature, and it's true, if you basically form an amorphous lithium superoxide, and amorphous lithium superoxide disproportionate almost immediately, instantly, within a second, and you form lithium peroxide and you release oxygen. But what happens if you stabilize this system and go this way? You notice here there is no oxygen. That's a closed system, like lithium-ion. Huh? And the energy out of this system is very, very high. So basically, because in the lithium air, we still need a tank of oxygen. That's a hit in energy right there. Huh? So what we decided to do is see if we can stabilize. We did some computing. My colleague Larry did the calculation to see if the crystalline phase of lithium superoxide exists, and if it exists, what are the energetics? Are they favorable for stabilizing it? So we went in to try to stabilize this phase in a crystalline phase, if you want, and see if it's stable. So we developed a technique where we put in iridium catalyst on RGO, reduced graphene oxide, as the cathode. You can see here these are clusters of few molecules or atoms, maybe 9, less than 2 nanometers. And the first experiment we did, we were very surprised. This is what you get without the catalyst. Huge polarization, basically the same like everyone is observing. But with this catalyst, we've seen a significant reduction in the polarization. And the cycle life was very good, and then it died because of oxygen crossover, that we don't have a membrane. So once we changed the lithium metal, when we opened the cell, we find basically a powder on the anode that's lithium hydroxide. So when we change it, refresh the lithium anode, we continue cycling this system, for almost 200 cycles. So the first thing we need to do is, what is the morphology of this new system? Because in the lithium air, the lithium peroxide has a donut type shape, like this. That's what you've seen in most of the publication. But in our case, we've seen a totally different morphology. These are basically nanorods, very small nanorods, and highly dispersed. But they are actually very close to the catalyst. When we look by TM, we've seen most of them are basically built on the top of the catalyst, which is iridium. So the second thing is what type of discharge product we are getting here, because it's very different from lithium peroxide. So we applied the advanced photon source, hard X-rays, and you can see we did not see the lithium peroxide, but we see a new phase, which is exactly like what we predicted by calculation, which is lithium superoxide. Since you see it, it's crystalline, obviously, and it stays stable for 7 days. It's not like, eventually there might be a disproportion with time, so it's stable. That was an interesting thing. And the next step was we run a Raman, and you can see the signature of lithium superoxide as well in this case. So those are the two proof, but we have to buy a DIMS because we try to publish this in Nature, and the reviewer will not accept this result. He wants a DIMS to show that there is one electron transfer. So I spent $200,000 to buy a DIMS, and we did, and we were able to show that it's one electron transfer, which is great. Now we have it. You guys are welcome to use it. It's an institute, and that was a proof that we do have one electron transfer. So how that happened? What is the reason why the superoxide, lithium superoxide, is stabilized? So we went back and looked at these electrodes, because we've seen most of them are at proximity of the catalyst. And we look at the catalyst itself, it changed. It became iridium-3 lithium. So there is a reaction. The catalyst actually changed in situ during the initial cycling. We have a different catalyst. But if you look at the structure of this catalyst, and look at the lithium superoxide structure, they have a lattice match between the two. So basically, the superoxide is capped on the top of the catalyst. And that's the reason why we've seen most of them, because the catalyst is highly dispersed on the top of this catalyst. That's mainly the reason why it's stabilized. So we did some DFT calculation, and we've seen actually when you have a crystalline phase of lithium superoxide, the energetic is very high. It's very difficult to disproportionate. We did also some DFT, density of state, to show that if you have a superoxide, it's half metal, it's conductive, so the dissociation is easy, and that's the reason why we've seen very good cycle life. While the lithium peroxide has a large gap, it's almost resistive. It's extremely difficult to dissociate. So now I go back to a single closed system. If you are able to make this, you can go this way, you get 1,100 watt-hour per kilogram. And then if you are able to go further by putting 2 electron transfer, you get 3,500 watt-hour per kilogram. So if you just get 10% of this, you basically reach the best lithium-ion that I show you in the first part, which is 350. So we decide to prove the concept. So if you just go this, you can reach 500 watt-hour per kilogram at the cell level with this reaction here. So we decided to prove the concept, and we did that using a new catalyst, which is cobalt oxide. It's not the best. As you can see here, the first reaction shows about 600 milliampere per gram. Obviously, we need to target 1,800 to get those 500 watt-hour per kilogram I'll show you. But it cycles extremely well. And you see through NMR, you move from lithium superoxide to peroxide and back. So that's the proof of the concept at the moment. So now we're working on a different catalyst that is not normal, because iridium or platinum is very expensive. We don't want to go back to the fuel cell problem to see if we can activate more capacity out of this system. So with that, I will conclude. I've shown you here that the electrification vehicle is really underway, so there is no return, regardless of Trump or no Trump. Need to reduce costs, which is critical. If you want to expand the electrification, cost is critical. I've shown you a new high volume, new high energy lithium-ion chemistry that he's going to apply it in a vehicle in 2 or 3 years. It's under production now. It's been licensed by 3, and there is more people who want to license it. I've shown you this system, which is totally different from what people have been doing by using a composite selenium or doping, because we went into, I think, sulfur 22 and selenium, which is pretty much like doping. The cost issue is no more an issue. We're using a very tiny amount of selenium, but that selenium gave you conductivity, and depending on the electrolyte, it can give you also stability. You don't have dissolution, which are the 2 main problems for sulfur system. And this could be the biggest things. We just started. I'm pretty sure other people will work on it, but we have demonstrated that we can use a closed lithium superoxide system that you use basically the configuration of lithium-ion to basically make a real high energy system that can give you much, much lower cost and hopefully can be used in your grid. All right, and thank you very much.
So thank you very much for this 1 hour lecture and a lot of new and exciting data. So now let's open to the floor, and if you have any questions for Dr. Amine. Yeah.
Thank you very much, Carol, for your very comprehensive and informative talk. Could you just provide us some perspective of solid-state electrolyte?
Oh, yeah.
Because some of the challenge in lithium-sulfur and lithium-ion, maybe the use for solid electrolyte can address some challenges.
Yeah.
Could you,
So there is a lot of work on solid electrolyte, but we have actually a workshop at the DOE to talk about what are the pro and con on solid. Obviously, the idea is to use lithium metal. If you use just lithium metal with one of these high, maybe I can stay here, one of these high energy cathode, you can achieve very high capacity, as you know. As a matter of fact, I do have the plot. The problem with the solid electrolyte is the interface issue, because you have one solid and you have moving cathode and anode. You can address that by putting a polymer or something that is flexible, that add to the energy, because you are using additional thickness. The other things is is very difficult to make pinhole-free solid. And people have shown that lithium will just crawl towards pinhole, lithium dendrite, and create issue. We've seen that across the board. You have to make a glass. Maybe that's the only way. And then there is a scalability issue if you want to mass produce this system. So there is a lot of, it's not something which is not impossible to fix, but there is a lot of challenge with it. And then the gain on energy, the other thing is also how do you put the solid in the cathode and anode. That's because these solid are heavy. So the energy will drop significantly. So you can see you have to look at all this and see if it works, depending on which solid electrolyte you use. But you still have to use some of these, maybe 30% of these in the electrodes, and 30% of a very heavy material. That's a big penalty on energy. Yeah.
Okay. Any more questions? From a student?
Yes. He's not a student.
Carl, one question related to the use of selenium. Does it help with the dissolution? As you mentioned, the electrolyte play a significant role in preventing the dissolution of sulfur.
Yeah. Well, if we use that electrolyte with sulfur alone, there is dissolution. So obviously, there is something happening with selenium that created. We don't know what it is at the moment, to be honest with you. We're working on trying to understand it. But when you have selenium, even traces of selenium as a composite, and with the right electrolyte, we did not see dissolution. But if you take that electrolyte and run it with sulfur alone, you can see it. You can see the profile also changing. Yeah.
So is there anything like you think really special with selenium? Of course, they are in the same column in the periodic table.
Yeah. But it creates a composite structure with sulfur. You have a phase diagram, you have tons of different phases, But initially when we designed it, it was mostly targeting the conductivity. Yeah, but then we find out it's the same things like if you use, for example, silanes, electrolyte. Silanes are where you cap ethylene oxide, I think I presented that. If you use that, the stability of potential went up significantly. If you just use ethylene oxide, it's lower. So, but we do not know. It's a good question, but we do not know what is the role in trying to, the selenium play in basically eliminating that dissolution when you use that electrolyte. We do not know that at the moment. Yeah, but that's something we need to dig into.
Okay. More questions?
Yes.
From the back.
Thanks for your presentation. And I want to know if you use selenium, because selenium is conductive, but you combined with the novel electrolyte. But I want to know the kinetics is first or not, the composite, selenium and sulfur.
Yeah, but when you mean the conductivity or the kinetics of
because you mean the novel electrolyte, this is solenoid to solenoid transformation, not like in lithium sulfur battery is liquid to solenoid. So the kinetics will influence.
Well, I show you the rate capability of the system is not that bad.
Okay.
Yeah, here. Even with very small concentration, you can see it's not that bad.
Okay.
Yeah.
I want to know the mass loading of this system.
Oh.
Yeah.
This is, I don't know exactly what it is, but it's very high because all the DOE program has to follow a specific mass loading, which is pretty high. I don't know, maybe 4 or 5.
Okay, thank you.
No, all the stuff I'm saying here is we use the industrial process of making electrodes. We don't use things by hand and all that stuff, yeah.
Okay, thank you.
Yes. Maybe I will give you the...
Thank you, Professor Amine, for your wonderful talk. So, as far as the lithium-sulfur battery system is concerned, you know, like many people are working on high mass loading sulfur electrodes.
Yes.
So, as far as I know, that the loading should be, real loading should be more than 5 milligrams per centimeter squared to have reached those 500 watt hour per kg energy density. So, now many researchers are using interlayer to do a high sulfur loading as more than 10 milligrams per centimeter square, and they are coating the interlayer with carbon, different structures, those sorts of things. So I want to know your opinion, like what about this type of the cell configuration which they are using, adding an extra separator layer, so that will increase the weight also of the whole cell, but apart from that, it has also drastically increased the sulfur loading. So considering all these facts, do you think that this is a very practical option to solve the lithium-sulfur battery problems?
Well, it's not going to solve the dissolution and, and the conductivity. Obviously, when you add the thicker layer, you not only are adding weight, but you're also minimizing the electrode. You know, if you have thicker, then you have to make thinner electrodes. So. Yes. So that's a penalty. The question is how much loading you add versus how much penalty you get. So those has to be calculated. You can use, design software to tell you that quickly. But the problem of dendrite from lithium metal or the dissolution is still there. Yeah. Yes. Now I didn't talk about it. There is a paper that we published recently in Nature Energy, where we started with Li2S using. I can send it to you. It's very clever, and we're able to achieve 12 loading with that system. Yeah.
Okay.
Okay. Thank you about your talk. I want to hear your opinion on how about the future of the sodium batteries.
Yes. Yeah. Well, I will talk about sodium in his workshop. Yeah. So yeah, what sodium is not going to make it in automotive, that's for sure, because the trend is energy. And sodium, maybe I have to pull this back. Sodium may be for grid application. That's where the opportunity is. If someone can figure out a way to stabilize the system to get the right cathode and anode. So in my talk, I'm going to show you some very interesting work on the anode side where we use red phosphorus. And we get some real interesting result out of it. So, and we also develop a tri-phase system that shows capacity is very close to the oxide lithium. Yeah. So a combination of these two can give you pretty high energy. But if you can do it with sodium, you can do it with lithium, which means lithium will be always the winner for energy and for automotive. But for grid application, yes, I think we should continue because I was in Chile last year. They say that they have tons of it. But when you talk about growth of 40% electric vehicle in the next 10 years, you're going to have a problem with not only sodium, lithium, but also nickel, even nickel. The cathode producers are very concerned about nickel because when the demand increases, the cost goes up. And that'll be an issue. Forget about cobalt. Cobalt is another story. But this too will be an issue when we have very mass production of, to basically achieve 40% full electric. That's 40 million or 50 million electric vehicle a year. And then you can calculate how much energy you need to power those. And then you can go back and calculate how much material you need. It's going to be a big problem. So sodium could be, people may go back and say we want less energy and sustainable low-cost material. And you may make it in electric vehicle eventually when you get to those levels. Yeah. But for grid, definitely yes.
Thank you for your nice talk. Of course, about the lithium-oxygen battery, you said that you could stabilize the lithium superoxide after adding the iridium. But then the battery was stable around 30 cycles, as far as I remember you showed.
No, yeah.
And then...
Yes. Yeah.
Yes. The previous
Yeah. So
yes.
basically we have about maybe 40 cycle.
Yes. So now my question is after that, you said that you could stabilize the lithium superoxide, but the problem of degradation of the battery after that is because the mechanism changed to disproportion again to production of the lithium peroxide, or
no.
What's the reason?
No, the reason why we have, you can see, you cycle and then a sudden drop.
Yes.
So what happened is oxygen cross over to the anode, and then it reacts with the anode, and we lost anode, become lithium hydroxide. So
Okay.
when we refresh the anode, we get another 40 cycle, and then we continue doing that. We had almost 200 cycle with this system. So it's not a disproportionation; it's the
So
impact on the anode.
disproportion-
If we have like a membrane that can basically stop oxygen from moving in, then we should see very good cycle life out
So
of this.
definitely no disproportion in this system.
I expect should be some,
Okay.
yeah, but it's not like immediate and severe. You see, we kept that superoxide for 7 days. We didn't see any disproportionation. Now, we didn't look at long term, to be honest with you, but through the cyclability, the main issue why we lost capacity here is because of the cross-overs. Yeah.
Okay, thank you.
Okay, any more questions? Yeah, maybe one more question.
Carl, many people have tried very hard to publish papers in address issues cathode for the lithium-ion and lithium-sulfur, right? Many people, just work on the cathode, but it seems to me that it's even more challenging to use lithium metal on anode because safety, because for dendrite formation, cause many issues, right?
Yeah, it's
How do you
just,
think?
it's just very difficult problem. The lithium metal issue has been there for 70 years, and there are very few people working on it at the moment. But now, I think there is a big problem in Japan on stabilizing lithium metal. And so using solid state is one opportunity, or using different other techniques actually to additives or even coating on lithium, or even reaction, surface reaction. There's many things happening now. So you'll very likely start seeing papers coming out. But it's just recently the effort has been picking up. Yeah. In the case of sulfur, if you use Li2S as a starting material, then you can use silicon, and that take care of the problem well, if you are able to stabilize the expansion of silicon. But you have that opportunity that you don't have to worry about. Yeah.
Okay, I think with that, let's thank Dr. Amine again for this very informative talk.